Welcome to the next session of the subject Engineering Maths, Chapter 2, Differential Equations. And we were in the concept solving non-homogeneous linear equations with constant coefficients. So we were discussing particular integrals. In the last session, we have completed three different cases in case of particular integrals. One is exponential function e power ax when a is not a root of auxiliary equation, and second one is exponential function when a is a root of the equation, and in third case we have seen particular integrals in case of two trigonometric functions. One is sine function and another is cos function. Now by looking at examples, the conclusion we have is if q of x equal to sine of ax plus b or cos of ax plus b, then my particular integral will be in the form a into sine of ax plus b into capital B into cos of ax plus b. Now this will be the general structure of my particular integral. In case of q of x equal to sine function or cos function when f of d square, that is d square is replaced by minus a square. In that case we should not get zero expression. So therefore whenever f of d square, that is f of minus a square, is a non-zero expression, and if q of x is either sine function or cos function, then my particular integral will be constant times of sine function plus constant times of cos function. Note this point. If q of x equal to sine of ax plus b or cos of ax plus b, if q of x equal to sine of ax plus b or cos of ax plus b, and f of d square equal to f of minus a square not equal to 0, f of d square equal to f of minus a square not equal to 0, then yp equal to a into sine of ax plus b plus capital B into cos of ax plus b, capital A into sine of ax plus b plus capital B into cos of ax plus b for some constants a and b, So therefore we have completed case 3 when the function is not equal to 0 when d square terms are replaced by minus a square. Now what happens when the denominator gets 0 when d square is replaced by minus a square? We handle that situation in case number 4. Now we have two different cases where d square is replaced by minus a square, and in that case the denominator expression will be 0. So one possible case is this: 1 by d square plus a square of sine of ax plus b. Now in this case when d square is replaced by this minus a square, denominator gets 0. In that case my result will be this: x by 2 into integral sine of ax plus b dx. X by 2 into integral sine of ax plus b dx. So this is x by 2 into integral sine is minus cos. So minus cos of ax plus b divided by derivative of ax plus b is a. So the answer is minus x by 2a into cos of ax plus b. Therefore in this case sine function becomes variable multiple of cos function. Sine is converting into variable multiple of cos function along with some constant minus 1 by 2a. But in case of case number 3, we don't have that situation. In case of case number 3, when you replace d square by minus a square, we are not getting a 0 expression. Therefore the result is constant multiple of sine plus constant multiple of cos. But in this case the result is variable multiple of cos. So that means the sine function will be converting into variable multiple of cos function. Now we discuss another case where denominator gets 0 when d square is replaced by minus a square. That is in case of cos function. So 1 by d square plus a square of cos of ax plus b. This is nothing but x by 2 into, this is common expression, x by 2 into integral of this function. So this is x by 2 into integral cos of ax plus b dx. So this is x by 2 into integral cos is sine of ax plus b divided by derivative of ax plus b is a. Therefore, this is nothing but x by 2a into sine of ax plus b. Now, in this case, when you look at this, the function cos will be converted into, the function cos will be reduced into variable multiple of sine function. In this case, the function sine will be reduced to variable multiple of cos function. So, when you are handling particular integrals, if the result is variable multiples, what does it mean? The denominator is getting 0. So even in case of exponential function, in case of case 2, the result is x power k divided by k factorial into 1 by f of d of e power ax. Of course, when you replace d by a, 1 by f of d becomes a constant expression. But before that constant expression, we have x power k by k factorial. So it's a variable multiple of exponential function. But in case of this, here also we are getting variable multiples of this. So therefore, we are getting constant multiple of some function means denominator will be not zero when d is replaced by a or d square is replaced by minus a square. We were replacing d by a in case 1 and case 2. And we were trying to replace d square by minus a square in case 3 and case number 4. So in case 1, what happened is the result is this. In case 1, the result is 1 by f of a of e power ax, constant multiple of e power x in case of case 1. In case 2, this is x power k by k factorial into 1 by f of d of pi of a of e power ax. So variable multiple of exponential function. In case of case 3, the answer will be a into sine of ax plus b into cos of ax plus b. So in this case, denominator is non-zero. That's why the result is constant multiple of exponential function. In case of 2, the denominator is getting 0. That's why the result is variable multiple of exponential function. And in case of case 3, denominator will not be 0 when d square is replaced by minus a square. Hence the result is constant multiple of sine plus constant multiple of cos. Even I told you, when you get both sine and cos, if f of d contains both even powers of d and odd powers of d. If it contains only even powers of d, you may get only sine terms or only cos terms. But if f of d contains both even powers of d and odd powers of d, then you get both sine and cos functions. Now, but in this case, when d square is replaced by minus a square, the denominator is getting 0. So therefore, f of d equal to 0 when d square is replaced by minus a square. The same case here also. In that case, sine function becomes variable multiple of cos and cos function becomes variable multiple of sine function. Okay. So write down this formula. Here examples are not required for case number 4. It's a simple issue. Now let us discuss case number 5. Suppose if q of x equal to e power ax into v, where v is a function of x only, then in that case, my particular integral will be yp equal to the basic standard formula 1 by f of d of q of x. So this is nothing but 1 by f of d of this q of x is e power ax into v. Now here we were finding 1 by f of d of product of two functions. It is a function of x, it is a function of x. Suppose if I have either plus symbol or minus symbol, what will happen? If I have either plus symbol or minus symbol, I can distribute 1 by f of d to e power ax as well as v. But in this case, we don't have that flexibility because we have a dot symbol between these two. Therefore, complexity can be reduced by taking e power ax outside f of d, but d is replaced by d plus a. So as an effect, when you take e power ax before 1 by f of d, this d is replaced by a, d plus a. So d is replaced by d plus a. Therefore, in this case, my yp equal to e power ax into 1 by f of d plus a into v. So simply d is replaced by d plus a. Previously, we have product of two functions. Now it is reduced to by finding a particular integral in case of a single function, that is v. That is v. Note this. Now we discuss one example to illustrate case number 5. So example is this. Suppose I am considering an equation d square minus 1 of y equal to e power x into cos 2x. Now this is in the form e power ax into v. Here what is v? This v is nothing but cos x. Now here let us try to find yp value. Yp is 1 by d square minus 1 of e power x into cos 2x. Now here a value is 1. So e power x you can take before this 1 by d square minus 1, but d is replaced by d plus 1 because a is 1, coefficient of x is 1. So d is replaced by d plus 1, 1 by d plus 1 whole square minus 1 of cos 2x. So therefore this is e power x into 1 by, this is d square plus 2d, plus 1 minus 1 gets cancelled, we get this. So cos 2x. Now this is in the form 1 by f of d of cos of ax plus b. So apply case 3. Here a value is 2. Therefore d square is replaced by minus a square. This is minus 4. When d square is replaced by minus 4, denominator is non-zero in expression. So we can apply case 3. Therefore in this case yp equal to 1 by d square is replaced by minus 4. 1 by minus 4 plus 2d of cos 2x. Therefore this is, its rationalizing factor is 2d plus 4. So rationalize this, 2d plus 4 divided by 2d minus 4 into 2d plus 4 of cos 2x. Therefore this is 2d plus 4 divided by, this is 4d square minus 16 of cos 2x. Again d square is replaced by minus 4. 4 into minus 4, minus 16 minus 32. So this is minus 1 by 32 into 2d plus 4 of cos 2x. Therefore in this case, of course we have this exponential function. So at the end I will multiply this with e power x. Okay. So therefore this is minus 1 by 32 into 2 times derivative of cos 2x minus 2 sin 2x plus 4 cos 2x. Therefore you can cancel out this 2. We get this as 4 by 32, 1 by 8 into sin 2x minus 1 by 8 into cos 2x. So this is only this part. This is simply 1 by d square plus 2d of cos 2x. But before that we have an exponential function. Therefore you need to multiply this with e power x. Therefore my final particular integral is e power x into this. E power x by 8 into sine 2x minus cos 2x. This is my final particular integral. Just we have applied the case 1. In this case, we have applied case number 5 as well as case number 3, because when you have cos and sine functions, you need to apply either case 3 or case 4, but in this case, case 3 works. Therefore, finally, we are getting e power x by 8 into sine 2x minus cos 2x. Okay? Work out this example. Now, before going to last case, let us discuss few important formulae. Suppose I want to calculate d power k of x power k. Here k is a positive integer. K is a positive integer. Here we know that d is nothing but differential operator with respect to x. So here powers are same. D power k of x power k. Suppose when you want d power 1 of x power 1, this is 1. D square of x square. When you differentiate x square one time, the result is 2x. When you differentiate this another time, the result is 2. So d square x square equal to 2. Similarly, when you go for d cube x cube, we get answer as 6. This 6 is nothing but 3 factorial. When you go for d power 4 of x power 4, the result is 24. You can easily verify. The first time derivative of x power 4 is 4x cube. Second time derivative 12x square. Third time derivative 24x. Fourth derivative is 24. Basically this 24 is nothing but 4 factorial. Therefore d power k of x power k is k factorial, where k is a positive integer. Where k is a positive integer. And second one is, suppose if this power dominates this. See, no doubt about these powers are positive integers. Here both the powers are same. Powers of d and powers of x are same. In that case, the result is k factorial. That means we are differentiating x power k with respect to x k times. So the result is k factorial. But when this number dominates this, then the result will be like this. Suppose if I write d power p of x power k, this will be 0 for all k greater than p. For all k greater than p, where k comma p are positive integers. Where k comma p are positive integers. When both powers are same, the result is k factorial. So when power dominates, when the power of d dominates x power, it becomes constant, so the derivative becomes 0. The simplest example we can go for is d power 5 of x power 4. When both powers are same, the result is 24. So this is a d power 4 of x power 4. So this is nothing but derivative of d power 4. When you differentiate this 4 times, the result is 24. So one more d is left, d of 24 is 0. So similarly, d power 6 of x power 4 is 0. So therefore, whenever this number dominates this, the result is 0. So this is one useful result. This is another useful result. Now I will generalize like this. The generalization point is like this. D power k of any polynomial of degree k. Any polynomial of degree k equal to k factorial. So d power k of any polynomial of degree k is k factorial. D power p of polynomial of degree k, polynomial of degree k equal to 0 for all p greater than k. Therefore, this is nothing but extension of this, and point 4 is extension of this. So write the points 1, 2, 3, 4 along with these examples. You can have this, you can cross check this, you can cross check this. So note the points 1, 2, 3, 4. They are very useful for the next case. That is, in the next case we were about to discuss particular integrals in case of polynomial expressions. Now let us discuss case 6, that is finding particular integrals for polynomial expressions. Now before discussing that, let us guess the result of particular integrals of polynomial expressions. Suppose when you differentiate x square, the result is 2x. When you differentiate x square, the result is 2x. When you integrate x square dx, the result is x cube by 3. This is a polynomial of degree 1. Because when you differentiate a second degree polynomial, the result is a polynomial expression with a degree lagging by 1. When you integrate a polynomial expression, the result is a polynomial but degree is rising by 1. Therefore, what we guess is, when you are finding particular integrals of polynomial expressions, the result is again a polynomial expression, right? Now let us discuss the procedure to find the particular integrals for polynomial expressions. So it is case 6, last case in particular integrals. Suppose if q of x equal to a0 plus a1x plus a2x square plus and so on plus ak into x power k, where ak is not equal to 0. Here I am putting restriction on ak because this is the coefficient of highest power of x. So when q of x is equal to expression like this. So in this expression we have two terms, powers of x, positive integral powers of x along with some constants. Such expressions are called polynomials. So when q of x equal to this, that is q of x is a polynomial of degree k. Q of x is a polynomial of degree k. Then my particular integral yp will be 1 by f of d of q of x, basic formula, 1 by f of d of q of x. This is 1 by f of d of, this q of x is nothing but a0 plus a1x plus a2x square plus and so on plus ak into x power k. Now how to handle this at this moment? So in order to get the particular integral in this case, what we need to do is, we need to take least degree term of f of d as common. So suppose in f of d, I go for some general example. Suppose if I go for f of d is d square plus 2. Say f of d is d square plus 2. What is the least degree term? It is 2. When you take 2 common, the denominator will be like this. Actually it is 1 by 2 into 1 plus d square by 2. Now when you take this 1 plus d square by 2 to the numerator part, this will be in the form 1 plus d square by 2 whole inverse. Now it is a series expansion of the form 1 plus x whole inverse. So now what is x value? X is d square by 2. Therefore apply a suitable series expansion up to power k only, because we were dealing with polynomial expressions of degree k. Even when you extend the powers, rest of the terms become 0, because when the power of d dominates power of x, the derivative becomes 0. Therefore take the least degree term of f of d, take the least degree term of f of d as common and apply a suitable series expansion up to the term d power k only, up to the term d power k only, right? Now let me write this point. Take the least degree term of f of d as common, take the least degree term of f of d as common and apply a suitable series expansion, and apply a suitable series expansion, apply a suitable series expansion up to d power k only. This is very very important, up to d power k only. Therefore, when you handle particular integrals of polynomial expressions, do this procedure, you will get the values. But the result is always a polynomial expression, because sometimes a degree may rise, sometimes degree may be lagging, but always the particular integral of a polynomial expression is always a polynomial expression. Okay, so work out this case. Now we discuss 1 to 2 examples on this particular case. So let us start with a simple example. Suppose this is a d square plus 2 of y equal to, for example, x square plus 4. Now it is a second degree polynomial expression. Here my yp is 1 by d square plus 4 of q of x is x square plus 4. Of course, this is the expression 2. Now here the least degree term is 2. So we can take 2 common, 1 by 2 into 1 plus d square by 2 of x square plus 4. So therefore this is 1 by 2 into 1 plus d square by 2 whole inverse of x square plus 4. Now it is actually in the form 1 plus x whole inverse. So what is the series expansion of 1 plus x whole inverse? The series expansion is 1 minus x plus x square, like this and so on. But don't confuse with this x and this x. So therefore I will change the terms. Here this x is nothing but d square by 2. So 1 minus d square by 2 plus x square means x means d square by 2. So d square by 2 whole square. If you have any confusion, take for example p. This is useful. Now 1 plus p whole inverse, 1 minus p plus p square of, like this, of x square plus 4. Now therefore in this case 1 by 2 into 1 into x square plus 4, x square plus 4 minus 1 by 2 into d square of x square plus 4. Here power is 2, x square. So therefore this is a second degree polynomial expression. D square of second degree polynomial expression, that is a d power k of any polynomial of degree k is k factorial. So in this case it is 2 factorial. Now this is a d power 4. D power 4 of second degree polynomial is 0. Therefore the expression in this case yp is 1 by 2 into x square plus 4 minus 1 by 2 into 2 factorial, this is 1. So therefore yp equal to 1 by 2 into x square plus 3. Therefore this is the particular integral in this case, but the degree remains same. Okay, just you may ask me why you gone up to d power 4, because here d is not d, actually it is a d square by 2. So in the future when some more terms join with us, so better to expand up to d power k. Here d is nothing but, it's not a simple d, here d is nothing but d square by 2. So therefore earlier I mentioned apply a suitable series expansion up to d power k. So therefore in this case my d is d square by 2. Therefore even if I write d as d square by 2, if I go up to d power 4, it contributes nothing. It contributes nothing. That means it won't give any value. It won't add any value to the particular integral. Therefore here d square by 2 whole square, that is a d power 4 of second degree polynomial is 0. So therefore in this case the result is 1 by x square plus 4 of 4 minus 1 by 2 into d square of x square plus 4 2 factorial. D power 4 of x square plus 4 0. So therefore the result is half into x square plus 3. See the interesting point, it's a second degree polynomial expression. In this case the result is polynomial, that is very clear, but degree is not changing. Sometimes degree may rise, sometimes degree may lag, but it doesn't matter, the result is a polynomial expression. Okay, work out this. Now let us handle one complicated example. suppose I have d square plus 2d plus 3 of y equal to, for example, x square. Simple second degree polynomial expression. The complicated issue is f of d because it involves three terms. So here yp equal to 1 by d square plus 2d plus 3 of x square. Here the least degree term is 3. So take 3 common. This is 1 by 3 into 1 plus d square plus 2d by 3 of x square. So therefore this is 1 by 3 into 1 plus d square plus 2d by 3 whole inverse of x square. Now you can call this expression as p. So 1 plus p. So here x power is 2. So I will go up to series expansion up to p square only. 1 plus p whole inverse. This is 1 minus p plus p square of x square. Now therefore this is 1 by 3 into 1 into this x square minus, actually what is p? D square plus 2d by 3. D square plus 2d by 3 of x square plus d square plus 2d by 3 whole square of x square So therefore this is 1 by 3 into x square minus 1 by 3 into d square of x square 2 plus 2 into derivative of 2 into 2x, it is 4x plus it is a plus b whole square. You will get a d power 4 terms. D power 4 of x square contributes nothing. Here b square, you will get 4d square. But 4d square by 9. So this is 4 by 9 into d square of x square 2. Next you will get a plus b whole square. A square plus b square plus 2ab. You will get next 4d cube. But d cube of x square contributes 0. Therefore I don't write d power 4 terms, 4d cube terms, but d square terms include. Therefore this is like this. Therefore in this case the value is 1 by 3 into x square minus 2 by 3 and this is minus 4x by 3 and this one is plus 8 by 9. So therefore this is 1 by 3 into x square minus 4x by 3 plus, let us simplify, 8 by 9 minus 2 by 3. So LCM is 9, this is 8, 3 2, so this is 6. So 2 by 9. Therefore in this case the result is again a second degree polynomial expression. Therefore this is the value of yp. Yp equal to this. Because here the complicated expression is d square plus 2d by 3. So I gone up to power 2. Inside d square plus 2d by 3 whole square. Inside this term you get 3 terms. 4d square term, d power 4 terms, d square terms, d cube. But d power 4 of x square contributes nothing. D cube of x square contributes nothing. But d square of x square contributes some value to the particular integral. Therefore when I go through this, I am getting a second degree polynomial expression, right? Now with this we have finished all cases in finding particular integrals, right? Now let me discuss few tips how to handle particular integrals when options are given in the examination, right? See, what we need to do is, generally when you are finding particular integrals in case of polynomial expressions, the procedure may be complicated when you take f of d as a complicated expression. Suppose in f of d, if you have d power 4 and d power 6 terms, the expression may become so complicated. So in that case, if the options are given in the exam, how to handle? Suppose if they ask you particular integral of an equation like this. Suppose my question is f of d into y equal to q of x. So they were asking the particular integral of this equation is option A, B, C, D. Options are given like this. Then what you do is, Let us try verify options. So I will consider f of d of, in place of y, I am taking option A. Apply f of d of A. So this is nothing but combinations of derivatives only. Purely apply many times derivatives with A. If you get q of x, so if f of d of A equal to q of x, therefore option A is right answer. So no doubt about this. Suppose if you are not getting this, then go with B. If f of d of B equal to q of x, then B is right answer. Suppose if it is not true, then apply f of d with option C. If it is q of x, then option C is right answer. If it is not equal, then C is wrong answer. Since it is not matching with B, B is not right answer, A is not right answer. So D is a right option. So simply you can verify options. But the difficulty occurs if the question may be like this. If the particular integral of this equation is, for example, yp of x, then what is yp of minus 2? So if the questions are given like this. So there can be two types of questions from particular integrals. One is a direct question. The particular integral of this equation is, four options will be given. Option A, B, C and D. So if options are given, you can handle very easily. Apply f of d for option A. If you get q of x, then option A is right answer. You need not verify for B, C, D. Because for one option, there will be exactly one particular integral. Because when we handle linear equations with constant coefficients, if they ask you general solutions, what we gone through is we have verified options. If equations satisfy boundary conditions, may or may not be right answer, because multiple curves may pass through a particular point, but in this case every differential equation will have exactly one particular integral. So apply f of d for option A. If you get q of x, you make it granted, so A is right answer. You need not go for B, C, D. Otherwise go for option B. If f of d of option B is q of x, then B is right answer. Otherwise verify for C. Otherwise D is right answer. If options are given, there is a chance for verification. But if options are not given, the question can be asked like this. If the particular integral of this equation is yp of x, then what is yp of some number? Then even if options are given or options are not given, you need to know the procedure to find yp. So always be cautious to find particular integrals, right? Now we discuss one general point and then we discuss one or two questions on classroom workbook if time permits in this session. Suppose if q of x equal to q1 of x plus or minus q2 of x plus or minus and so on plus or minus qn of x. That is RHS expression is q of x. So RHS is a combination of n functions with plus or minus in between them. Then my yp equal to standard formula 1 by f of d of q of x. So therefore this is 1 by f of d of my q of x is q1 of x plus or minus q2 of x plus or minus and so on dot plus or minus qn of x. So apply particular integral for all functions and insert the same symbol what we have. So therefore in this case yp equal to 1 by f of d of q1 of x plus or minus 1 by f of d of q2 of x plus or minus and so on plus or minus 1 by f of d of qn of x. Basically this is called linear property. This is called linear property for particular integrals. Linear property for particular integrals, because it is a combination of derivatives and integration. We know that derivatives follow linear property, integration follows linear property, right? So work out this. Linear property means when you have two functions or three functions, in between them you can have either plus or minus. So when you are applying derivative of that complicated expression, split that into three different functions, find the derivative of individual function and apply the same symbol. The same rule is valid even for integration also. Therefore, when you are finding particular integral in case of complicated q of x, that is q of x is a combination of n number of functions with plus or minus in between them, then yp equal to 1 by f of d of q of x. This is 1 by f of d of this. So between all these n functions, we have either plus or minus. That means you find particular integral for the first function. If it is plus, write plus. If it is minus, write minus. Plus or minus 1 by f of d of q2 of x. Like this, you can find n particular integrals for small versions of functions. Okay, this is called linear property. Note this. Now let us start classroom workbook. At least we can solve one question in this session. Let us start the classroom workbook with question number 45. Question number 45. What they asked is the particular solution of, basically here particular solution means it's a particular integral. So the particular integral of d square y by dx square plus 3 dy by dx plus 2y equal to 5 cos x. So right side we have a function in terms of cos. Now therefore you can handle this by using case 3. So here what is my yp? Yp equal to 1 by d square plus 3d plus 2 of 5 cos x. So 5 is a constant, dot is there, you can take 5 outside this 1 by f of d. 5 into 1 by d square plus 3d plus 2 of cos x. Now here a value is 1. So d square is replaced by minus a square, it is minus 1. So this is 5 into 1 by minus 1 plus 3d plus 2 of cos x. Therefore this is yp equal to 5 into 1 by 3d plus 1 of cos x. Now its rationalizing factor is 3d minus 1. So multiply this expression with 3d minus 1 and divide with the same. So therefore this is 3d minus 1 by 3d minus 1 into 3d plus 1 of cos x. So therefore 5 into 3d minus 1 by 9d square minus 1 of cos x. Again replace d square by minus 1, minus 9 minus 1 minus 10. So therefore 5 by minus 10 into 3 means 3 into derivative of cos x minus sin x minus cos x. So therefore in this case my yp equal to, this is 1.5 into sin x plus 0.5 into cos x. So this is my particular integral, 1.5 into sin x plus 0.5 into cos x. The function here it is cos x. So answer may be in terms of sin or cos. Here you have d square terms and d terms, odd powers of d and even powers of d. That's why the result is in terms of both sin and cos. Therefore the answer for this question is 1.5 sin x plus 0.5 cos x. So option A is right answer. Note this. This is the end of the session. Thank you so much. We continue classroom workbook in the next session.